Let's see. There it is. And now we're hitting the search. So, can you see me? Can you hear me? Maybe so. So, this over here, our new waiting room, at least this week, this month, that is Fork Bomb running on the Quiet Box. And there's the surge. This is HD size, so 1920, 1920 by 1080. Width by height is some 2 million and change individual pixels, each of which now corresponds to a site, an atom. If you look at the edges, it looks kind of choppy. It's made up of all these little diamonds and stuff. Each one of those diamonds is an event window, is 41 pixels in a little diamond shape. And this thing has now been running live for 2 minutes and 12 seconds. And at the moment, VidServe is still behind the firewall, so it's just for the local network. But hopefully there'll be some time in real business. We can come back and look at this some more. I'm just going to let it run for now, but I'll get out of the way and let the waiting room music take over. looks like live audio is okay too. Ooh, ooh. Everybody, it's T2sday. We are here in the waiting room looking at a live stream of a cellular automata simulation that's running on the TENS torrent quiet box called Roses BH. That's the name of the Living Computation Foundation quiet box. And you know, this is fun. This is live. We'll look at this a little bit more later, assuming there's time. But I just wanted to start there. Okay, life tries. It's the progress report of the T2 tile project, where we're trying to build an entirely new computational architecture from the low-level hardware principles to software, and we're trying to give up on deterministic execution. We're trying to give up on the idea that every step has to be perfect or else it's chaos. Life doesn't deal with that. Life tries. That's its signature characteristic. If something's out there trying, if you think it's trying, it's living. Living equals trying. Trying equals living. Living means trying. So that's my sort of philosophical ground for this month. I had a lot of moaning and groaning. I'm going to try to spare you as much of that as I can. Okay, so here were the goals. Display, how did this all, well, whatever. Okay, let's just jump to the results. Display T6 ring EWs. What the hell is that? Well, T6 is the TENSX tile. It's the shorthand for the TENSX tile. Those are the individual little processors that are running in the live stream that's going behind us. The live stream behind the live stream. The simulation live stream. I don't have a good display of that. It's a text display, but it's okay. I feel good about that. Consider regional hubs. We'll talk about that today. Live stream sim to the world. I colored that green because we did do it. We did the live stream, the simulation. The to the world part is only indirectly true because we can go over here, and that's live streaming the simulation to the world. It's just going via about 6 bounce shots, and so people can't connect to it directly as yet. Find fun in this POS world we're in. You know, I did okay considering how much absolute terrible stuff is going on in the world, but I did have fun hacking on all this stuff, and I made a little bit of progress. So let's take a look. All right, so I don't want to spend a tremendous amount of time on the software timeline. I've gotten some hints from friends who have my best interests at heart. You know, they have to kind of admit that, you know, the software stuff is not as exciting. And they liked it back when it was software guy lost in hardware land, and I was trying to physically build stuff because it was easier to relate to. You know, they're too heavy, they're going to break, you know, stuff like that. And, you know, I agree. I think it was more fun when I was trying to build new hardware. But, you know, this is all in the greater purpose. This is all in the mission of life, to the mission of Dave's life, you know, to make something, do something by itself. And, you know, there's a big component for research purposes that we're using software to do that with. So we'll see if we can manage to try to cram more hardware in there, but I'm going to try to race through the timeline as a result, and I'm just going to focus on stuff that I achieved as much as possible. I mean, there's some bugs that I just can't get past. Knock one working, so that was 22 days ago, nearly a month ago. In the black hole T2sday tiles, in the black hole chip framework, knock, well, in lots of these machines, knock stands for network on chip, and so it's connections between local neighbors that are really wide and really fast, and the T2sday tiles have two of them, knock 0, which goes east and south, and knock 1, which goes west and north. So I did a bunch of stuff like that, and finally started to get the T2sday tiles talking to each other instead of just talking to the host. 20 days ago, all right, so I've been mentioning this thing about, regional hubs. What does that mean? I'm going to talk about that today. I got to hurry up. But in order to do this regional hub idea, the T2sday architecture, they call it SPMD, single program, multiple data, and that's to be distinguished from single instruction, multiple data, because each program, although they're all the same, can be running at different places at different times. They don't have to go in lockstep like they do in the traditional GPU architectures. But the architecture itself is not restricted to single program. So if I wanted to do, have these T6 tiles doing this program load and those others doing something different, there's nothing that says I couldn't do that. So an image block was the structure I started to make up to describe a program image, to describe an image that could be loaded into a T6 tile. T-18, I got it implemented. Consider sending event window transitions between T6 tiles. So again, we'll talk about the architecture in a minute. Once we had T6 image was a structure, we had to have an image manager to keep track of all these different program loads. It was a big pain in the butt, but got it working 2 weeks ago. Then, okay, if we're going to be able to have multiple programs, we have to be able to create a new program to run on the T6 tiles so that we can then say, this tile should use A, this tile should use B. So I built a configuration file using the TOML, or Tom's obvious markup language, and a week ago, discovered I'd fucked up an absolutely basic C++ operator implementation in one of the chord classes, and it had lain there not being found for, I don't know, weeks, at least weeks, probably months. And okay, well, so then we need to fix that. Also, I invented a new structure which I called cell. Perhaps that's unwise. I mean, I was getting pushback for using the word image to mean a core load, a core image, because, image means images, pictures, right? Well, cell means like an individual site in a cellular automata, whereas cells that I'm talking about here, they're much, much bigger. 6 days ago, go see if we could actually do this idea of creating a new program and having it run on some of the tiles while other programs run on it. And we made a new T6 image called Zot, which actually does the same thing that the event window processing image does, but it has a different name. It could be different in the future. I spent a whole bunch of time in the last week trying to find a low memory overwrite bug without going into the details. This was a bitch. And why did it happen? Because I got careless. Before I figured it out, actually, I went to the trouble of rebooting Rose's BH, the quiet box itself, which had been going for some 60 days or something like that, because I thought, how is this happening? But it didn't fix the problem. Eventually, I fixed the problem 3 days ago, and so then it's like, what am I going to show? Well, I said, well, what could I do quickly? And the idea was, well, hey, I could make a little graphical display. I have all the bits and pieces for that. That would take place just at the high level C++ stuff to rasterize out the things, and then Python stuff to push it all around to FFmpeg and so forth. So I started working on that, and that's what we were seeing at the beginning of this episode. First cut live stream running on the quiet box, make it visible in the T2 rating room. That was yesterday. That was about 12 hours ago, or maybe a little more. And less than an hour and a half ago, I got these slides together. So there we go. So what I wanted to do today for some actual content was to revisit the whole idea about what I've been doing with the quiet box so far since August when it arrived, and what's coming up next, because it's a big shift and it seemed like an opportune time. So I got one of those drawing tablets for my birthday, so I've been really getting a kick out of drawing pictures with a pressure sensitive stylus, so you can have big fat lines and little bitty lines and so on. So one view of the quiet box is there's an x86 host, a traditional computer CPU, powerful one, that has these 4 black hole cards plugged into it, and each black hole card has a black hole chip on it, 1 black hole chip on each card. The chip can burn up 300 watts all by itself, so it's not like having only 1 chip is that terrible a thing, although some other ones have multiple chips. And each of the black hole chips has 140 T6 tiles on it. So I thought, like in 2 days ago, 1 day ago, I got an email from Tens Torrent support. Hi, David, you're receiving this email because you own, this whole thing has got jaggies. We're going to have to put up with that. I'm sorry. I've got some kind of duplicate something or other going on there in my thing. Starting February 4th, in other words, tomorrow, firmware blah, blah, blah will change the core count on each P150 card. That's the cards that I bought, that I paid for, that I'm using, to a 120 core configuration instead of 140 cores. Instead, 120. So a software update is going to take away 20 of my cores on each card. That means 80 of my cores altogether are going to go poof when I update to firmware 19.5.0. And the email has the gall to say, oh, what's the expected impact? Minimal. Typical workloads show a non-material 1 to 2% performance difference. Now, of course, this is rich, given that blabbing about how many cores they have is their whole selling point like that. So now they can say, oh yeah, we'll take away 20 cores, and you'll hardly even notice. And so instead of this, it's actually more like this. Now with the new firmware, 140, no, 120, another 140, no, 120, so on and so on and so on. This double imaging is really very irritating. But I'm not going to mess with it. So long and short of it, I expect to not upgrade to firmware 19.5.0, whatever it was, unless I absolutely have to, because as they admit in the email, if you were depending on specific core counts, you're going to have to modify your code. Yeah, I'm depending on specific core counts. So that was fun. But this is the picture that I was going for, that there's a, from the, what's the next one? Okay. So here's the black hole chip. There's a T6 tile on it. There's 140 of them on mine. But they don't have direct connections to that x86 host, they go by this PCIe bus, which is, again, wicked fast and super cool, but every single thing that a T6 tile wants to send to the host has to go through the NOC, the network on chip, step by step by step by step, until it reaches the PCIe interface, and then it goes zip up to the host, and so on. And then, you know, so here's an individual T6 tile blown up, and so is it possible that I dare try to fix this? So that's doing it live. So, you know, this something like this is a typical picture, but that's not the way I think of it. You know, the way I think of it is more like this. We got the x86 host. It is in charge of space. It in its main memory, it has the position of all the atoms in the cellular automata grid. In the current code that's running now, that what we saw at the beginning, the purpose of the host is to rule space, to know the organization of all the individual little atoms. And then all of those little T6 processors out there, they don't know where anything is. They get told, here's a little diamond shape called an event window, and it looks like this. And given just this much, you can't look at the rest of it at all. Just looking at this much, what should the result be? And what we're running is fork bomb, where if you have a fork bomb element atom in the middle of the event window, afterwards it just fills up the whole event window with fork bombs. Yay! Like that. The host controls the space. The T6 tiles collectively control time as state changes. And that's a problem because everything has to go back and forth between the host and the T6 tiles. So there's a bottleneck here, which is another version of what's called the famous von Neumann bottleneck. It's a slightly different version, but it amounts to the same thing. And that's why the architecture that we're looking at now was only meant to cut our teeth. It was only meant to look how, to get to know the hardware. And it's served that purpose. And okay. So I've been talking about this regional hub idea. What if the idea of having a little centralized thing that keeps track of space and having little individual processors that just do transitions, what if that's not a bad idea? It's just an idea that you shouldn't use globally because you get that bottleneck. But if you just had a little hub, a little regional hub that had maybe, 8 little event window processors surrounding it, it was just going back and forth between them, then it wouldn't have such a bandwidth problem. In exchange, we're going to have multiple hubs, regional hubs, and they're going to have to coordinate with each other to send back and forth the results of what their little collection did. An approach like this has a lot of advantages. We'll see some of them going forward, maybe not this month, but as we develop it out further. Here's the configuration file, and we can say, okay, cell 3.3, it's 3 by 3, fill it with event window processors at 1.1 in the cell, put in a hub, it's 2.2, there's Zot, the new image we made, the third actual program image that we can download. This is all running. I was using my drawing tab to try to figure out, so now each of these big areas here is the region around a cell. So it's a bunch. Those are not individual cells anymore. Those are now Tenzix tiles that have control over events in a bunch of them. All right. So let's take a look at Fork Bomb a little bit more. All right. So we've got all this churning around. What's happening here is all of these colored twinkling things are instances of Fork Bomb. And all this black stuff up here is instances of empty. And we have a bunch of emptiness here, even though the simulation's been running for over a half an hour. Because I built, it got a little boring after Fork Bomb has taken over the entire grid. Again, this is 1920 by 1080. it just sits there churning, which is fine. Yeah, it's happy about it. But I built in a mechanism that just uses random numbers, and every so often it drops nuclear bombs. It just erases big or little circles all over the place. Look, there it goes right now. I didn't do that. That's auto atomic technology, thinning the herd. That's a small new event. And immediately the fork bombs just continue growing back in. Why are they twinkling? They're twinkling because in each fork bomb element I put in a counter, and every time a particular element, a particular atom of fork bomb has an event, it increments the counter, and then the color is a function of the count. So as the count gradually increases, the colors come and go and so forth. So when you see a big region that has a region of different color, the count in all of these regions is kind of similar to each other, but kind of different it was over there, and so on. So, especially with the big nuclear bombs, which we haven't seen just now, there is a risk that they could all be wiped out. I've never seen it happen except when I just sat there with my finger on the big nuke button, but it's possible. Okay. So, right, and here's a little zoom in on the way I look at the world. The T6 tiles, we rule time. So there's, get my face out of the way, there we go. So if we have an atom of fork bomb in the center, and then after the transition is done, we have the entire event window is full of it, and that gets sent back to the host, which writes it into the appropriate place in the grid. And okay, so that's it. Next time, EWT, Event Window Transition. So one of the things that's kind of fun about all this for me is that an event window transition, a before and someone fills in the after, is this nice little unit. You can just throw it out and let anybody work on it. And that's what makes having a whole bunch of event window processors, EWPs, a powerful idea, because an event window transition it's 82 individual atoms, so it's not tiny, but it's not huge either. So I want to get this regional hub idea working. It's pretty ambitious. There's a lot of stuff left to do. And then I want to start looking down the road a little bit. I mean, where we are now, when you want to implement fork bomb or drag and res or any kind of particular physics for atoms to have in the simulation, you have to write them in C++ at the moment, and it's very low level code. So want to think about trying to get to more convenient languages to write more complex behaviors, because that's where the movable feast machine shines. Keep on drawing stuff because that's fun. And hopefully find other fun stuff too. So that was my January. Also, I did have to, I went back and got some additional medical testing, which apparently is okay. So apparently I'm okay. And that is it. I hope to see everybody next month. And there we are. Can I get the window up here? Yes, I think I can. There it is. And yeah, size speed, 80 cores. Just give them up. What it kept making me think of, when I was a kid, I saw a Japanese science fiction movie. I did a little searching a couple of days ago trying to find it. But I couldn't. It was a live action thing where there was, as I recall, it was a robot, a humanoid robot, and it was in danger. It had a super terrible opponent of some sort. And so part of the key to its success was it has this idea that I will reprogram myself to be bigger. And that's what it did. And, you know, even when I was a kid and I barely knew the difference between hardware and software, that already struck me as pretty funny. You can reprogram yourself using software to make yourself physically bigger. That's hardware. And yet, tends toward, I'm going to reprogram myself to take away a bunch of your hardware. And, you know, I think really what's going on is, I was worried that maybe they had found that it's drawing too much power or something. It's not reliable. I don't know what the name of the robot was, but in the old Japanese movie. But I really don't think it is. I don't think there's any actual hardware reason why their firmware is doing it. They're just trying to reduce their software burden. They're just trying to only have to support one set of counts instead of doing parallel counts. And now that may be because their yield is low on the black hole chips, and as a result, it's not worth them doing a whole bunch of extra software work, which is expensive, to support 120 cores versus 140 cores. Now, you might think they could have just, abstracted that away, but, especially down at the lowest level, everything costs. And I understand that. I absolutely do. That if you could settle on 120 and then never have to worry about any other size in the black hole family. I mean, of course, wormhole is already a different size, and the next generation almost surely will be a different size as well. So I downloaded what I believe is the last version that doesn't do this, So Giant Robo, that was an animation, right? The one that I'm trying to remember was I thought live action, but maybe not. And anyway, so hopefully there won't turn out to be any showstoppers. And, they point out that if I wanted to grow it later and buy a whole bunch more quiet boxes or buy black hole cards bulk and start plugging them into my own frameworks, I would want to have the new firmware. So I would, they're telling me I should bite the bullet and give up on 80 cores. I can't do it. I can't, especially because 80 cores, each of those 10-6 cores is actually 5 individual tiny little CPUs. It's actually a little 5-core multiprocessor for each of those 10-6 tiles. So it's actually 400 cores. 80 times 5? Is that really right? 64 plus 8, 72. I can't do arithmetic to save my life. 5 times 80. 5 times what is 40? 400 little hardware threads. And so, all right. And so that's one thing. And the only other thing, so thanks, folks, for stopping by, for coming here live, because it jazzes me up a ton. Thanks, Pun Master. Yeah, I mean, so, getting older day by day, but that's the best scenario. But let's go back to, okay. And so I'm excited about this because there's another auto atomic technology bombing going on. Again, that's a small one. The way it works is if it picks a small one, it does lots of little ones, and if it picks a big one, it does a few really big ones. I'm really excited about this because it is live. I've been showing you and the world time lapse of the T2 tiles for years. I mean, it might, well, not for the T2s, but for all kinds of things. And is this going fast enough to be watchable? Well, barely. It was way too soon, but I actually did try to take some measurements and figure out, there's a big nuke. So now I can peek through here. Hello. And again, just immediately, and all that raggedy there, all those little diamonds, those are one event windows each, because the fork bomb fills the event window whenever it gets a chance. So surely I want it to go much faster than this, in particular because fork bomb physics is so simple. I mean, all you do is take the guy in the center, you increment his counter, because like I said, I built that in, and then you copy the entire event window and you're done. So the speed of this that we're looking at, it depends almost not at all on the complexity of the fork bomb physics, because it's so simple. And we later on, like with the diamond replicator that we usually see in the waiting room, that has a huge pile of code that executes every single time, checking all these various invariants and restoring stuff, healing things, everything, ton of code. And that's going to make this stuff look like it's going super fast by comparison. So that's scary. And my estimation, oh, okay. Well, see, again, even with another big nuke event, there's still plenty that's there to repopulate the herd. So this seems scary slow, but I do have a few little tricks in my back pocket, and I'll share them with you, my actual live stream fans, live stream friends and supporters. Thanks for being here. This is only running one black hole card. We've got 4. I've tested the configuration with 2, 3, 4 various things. You can just set that by changing the dtoml configuration file now. This is running on one black hole card, and the T2sday tiles are only running at 800 megahertz, even though they're capable of running at 1.2 gigahertz. So we have a 50% bump in speed yet to use. And when you bump the speed of the T2sday tiles, you also bump the speed of the nodes. You bump the speed of the networks that go between all these things. So I have not dealt with that here because this is going to be bottlenecked by pushing everything in and out through the PCIe tile, going back and forth from the host. That's a tremendous amount of data being pushed a long distance from the point of view of any given T6 on a given black hole chip. So I'm hoping that we'll be able to go faster than this, even with more complex physics, once we get the regional hub going, where we're taking small ranges, 8 or 15 tiles to be event window processors with one hub to collect their things and to talk back and forth with it. It's going to take a couple of months. It's a big hack, but made a good stab at it. So that is my feeling. Oh, and I guess the bottom line is, as best as I could figure, just by measuring, 48 minutes, I'm not displaying statistics at the moment, but I have an overall, a number of events. So taking the total amount of time, taking the total number of events, dividing it by the number of cells we have here, the number of sites, which is 1920 by 1080, divided by the total number of events, divided by the total number of, divided by how many seconds the thing has been running. That gives us the average events per site per second, and that's called an error. One event per site per second. If we could build a machine that could deliver one event per site per second on average to some big pile of sites, that would have a 1 error rating. And the 1 error has to be considered relative to how big the grid is. So a 1 error on an HD grid is not as impressive as one air on a 4K grid, which is not as impressive as one air on an indefinitely scalable grid, which is what we're really trying to go for. But here we're taking the, the intermediate step of saying, okay, we have this much hardware. Let's see how many sites we could handle and still get an average event rate, an AER, as high as possible. And on the T6 tiles, I was coming up with estimates of, we were getting one air? No, we're not getting one air. The appropriate unit is a milliair, a thousandth of an event per site per second. Or to flip it over, it means an event will, an arbitrary site will typically get one event every 1,000 seconds. So that's super slow. And that's why I've had to do time-lapse for everything. So my guess here is that what we're looking at is something like 150 milliair. And again, don't hold me to that, because number one, it's very rough calculation, and number two, we have a ton of work to do. So I don't know if we can get to one air. One air is really big for if you're going to have a serious number of sites, and I really want to stick to an HD size grid if I can. So that's where we're at, and I'm excited. I'm worried about how long this is all taking, but I still feel like there's progress happening, and there's places that we're heading that I still think they're worth heading for. We shall see. And that's it. So let's see. Raising adventure. Yeah. Okay. Yeah. That's a little bit of an Oops. Tried to click on the dark. Need to pun on AER. Average event rate. So something like, oops. Event rate, yeah, so AER, which I pronounce it air, so, it certainly makes sense that you could think ERR, but it feels like it's Irish to me, like it's Gaelic, how's the air? Or something like that. There you go. Thank you. And I'll put I'll put hearts on it myself. For that. Oh, can I put a reaction on it? I don't see any way to put a little plus on it. Anyway, okay. So that's it. Put user in timeout. Yeah, that'd be a good idea, huh? Okay, so I'm gonna shut this down. Live stream is at 54 minutes or so, and I'm tired. I didn't get enough sleep last night. A question. How many layers or hubs or communication layers do we have? Yeah. I'm intending to start out with one layer. Well, actually, that's not even necessarily true. I'm just going to say this out loud, though. So I'm imagining a cell size of like 3x3 or maybe 4x4 or 5x5, something like that. And and tile an entire black hole card with them. Now, we have to use a different method for black hole card talking to other black hole cards. They don't have direct spatial connections. They have very high speed. Yeah, and Wayne, that's absolutely right. The math, the official math of average event rate is meant to be for an indefinitely scalable machine. And by going hierarchical like this, I'm buying a little bit of architectural trade-off. So even though I have, say, 9 processors all working together as a single region, and any of those processors might be doing any of an event in a significantly larger space in the memory of the local hub, it still isn't doing an event from miles away. So it's still spatial, but now it's at a higher granularity. And one of the typical ways that you do it in traditional system design is you go hierarchical. So after you get so many cells, you now make a supercell, and then you make a super duper cell, and so forth, and you make a multicellular creature that has organs and all sorts of upper level structures on top of the fundamental organelle or cell bottom, whatever your particular hierarchy is based on. In order to come up with an honest estimate of the AER, if you're going to measure the official indefinitely scalable, and I think you know this, but it's just an opportunity to review. Officially, to come up with indefinitely scalable AER, which is what we really want, you have to, what you do is you take a machine of a given size and you measure how fast it can do events averaged over the entire thing. And then without changing the architecture, you somehow make the machine bigger and you measure the average event rate over that thing. And you keep making it bigger without changing its underlying architecture, which means you can't add new levels of hierarchy in hardware as it gets bigger. You can do any kind of communication you want in software. So you could build a virtual tree with a virtual communication network if you want, but the individual things are getting further apart, which means to cross the entire grid, if that's what you think you need to do, it's going to be slower and slower and slower as things get bigger. So we are talking about, so that's average event rate indefinitely scalable. Start with a small machine, measure how fast it goes. You grow the machine without changing the architecture, see how fast that goes. And you keep on growing it until the average event rate converges. And at that point, the claim is you've washed out any effects of getting, special treatment by the fact that the grid is fixed at a certain size. And instead, you've tested the architecture over an arbitrarily large version of it. Or that's what the estimate would be. With a finite average event rate, so AER sub HD, that's what we're going to go for here. And we're going to try to get, I would 250, 500 milliair. Could we get 1 air on fork bomb on an entire quiet box? So that means including having to ship data between black hole cards through those ultra fast Ethernet cables that we saw sticking out of the back of the black hole card. Speed of light, yeah. Well, I mean, yeah, absolutely. The speed of light measure for communication from the farthest communication path. Yeah, that's a good lower bound. That communication's not going to go any faster than that. Or if you're going to assume a clock rate for communication, in which case being able to get from anything to anything is supposed to be able to happen in 1 clock time period, then it's going to get bigger and bigger and bigger, and it's going to be bounded below by the speed of light between the diameter of whatever your physical hardware is. Absolutely. And we're not going to come anywhere close to that, although the 800 gigabit per second, Ethernet connections that the Quiet Box has between the black hole cards is pretty close to the speed of light compared to the serial protocol I made up, the 1-bit serial protocol that I made up for the T2 tiles, like that. So, you know, distinguishing between indefinitely scalable air and finite air is really important. I expect if we get traction here and other people start working on it, and, you know, in the third conference on movable feast machines in 2029, or something like that, people will be reporting achieving 1 air on XYZ and so on and so forth. If you see nested loops as layers, then even there, 32 is pretty much the limit of layers. Yeah. Okay. I sort of see that. I see nested loops as being a time-bound feature, and layers, in a neural net sense, as being a spatial-bound feature. And there's lots of ways to trade back and forth between time-like computations by becoming more sequential and space-like computations by becoming more parallel. So, you know, you can see nested loops as layers, but indeed you have to pay the piper. You always have to pay the piper. I mean, for example, the T6 tiles, the T6 tiles, they have a vector accelerator built into them that is 32 lanes. So they can do a bunch of operations in parallel at times 32. And, you know, each T6 tile has a big pile of silicon dedicated to that. And I'm not using it for anything because mostly the extra silicon for doing all that stuff is aimed at floating point. We may yet use floating point down the road here, but so far it's good old integers. Okay. Clock cycles it takes to get from those places. Yeah. And I want to argue that eventually, if you're going to, I don't know the best way to say it. The idea of having a tile where you're supposed to commit to the tile hardware up front, and then it's frozen. And then you optimize the hell out of it, you shrink the line width, you do all the stuff that you can until each individual tile is teeny tiny, cheap as sand, you know, and so forth. And if you can build software that'll run on that kind of architecture, it'll run on just about anything. And that's the point. That's what robust first means. If you can come up with more or less any mechanism of doing event window transitions, and you can come up with it in some kind of semi-parallel, semi-centralized way, which is the regional hub idea, then, you know, still, as the machine gets bigger, it's got to get slower. That's kind of Spencer Brown laws of form stuff. Because just as you say, Wayne, you know, light speed is a boundary. To cross a physical object takes longer the bigger the object is. Have a nice day. And so you know, so we deal with that. But in exchange, if we can get an indefinitely scalable architecture, then in principle we could be writing element transition rules, element transition code. We could be writing physics that describe how an event window that looks like this before becomes an event window that looks like this after, and it's up to somebody else to figure out where the before came from and where the after goes. And you know, we'll take it from there. Okay, well, thank you, folks. Thank you for chipping in thoughts and questions and great puns. There are some old memories here. Well, I mean, so we talking, I'm sure there are old memories everywhere. That's the signature feature of memories, is that they have information about the past contained in them, which again is a time for space trade-off. something actually happened way back in the past, and happened through time, and that created memories which are somehow stored spatially, but can be retransmitted. Can be reformed into code, and the code can be transmitted, or an action depending on it can be enacted, and so on and so forth. Okay, thank you, everybody. I guess we'll stop it here, and this was great. I hope you had an okay January, considering everything. I hope you have an okay February coming up. I hope to see you in March, step by step. Okay, that's it.